This is part 2 of lesson 8.02. How long does it take for a sample of an isotope to decay? When a radioisotope, a single atom, decays, the original isotope, called the parent isotope, changes into another isotope called the daughter isotope. In a single atom, this change takes place almost instantaneously. However, scientists are often interested in how long it takes for a sample of the isotope to decay. In other words, if I'm holding 5 pounds in my hand, every single atom will not change at exactly the same second, exactly the same instant, even though when an atom does change, it takes only an instant to change it. All right, so let's check out this graph. So we have number of uranium-238 atoms, and we have millions of years. One half-life is 713 million years. So it shows here that I have a sample, and it's pure uranium. All right, so after one half-life, after 700 million years, half of my uranium has changed into thorium. So thorium is the light grayish green dots. Okay, now after another half-life, after another 700 million years, so I'm at about 1400 million years, that half got divided in half. All right, so if I'm right here, and there's 100 atoms that I started with, so I have 100 uranium atoms, I take half of that, and now I have 50. If I take half of 50, now I have 25. Okay, I take half again, and now I have 12 or 13, right? Because you can't have half an atom. Okay, now after 4 half-lives, okay, now you can see I just have 6 uraniums left. 4 half-lives is about 2,800 million years. After 5 half-lives, you can see I just have 3 remaining. After 6 half-lives, I have 2. And after 7 half-lives, I have 1. And so I need another half-life to have it all gone into thorium. All right, so another example is carbon. Carbon's half-life is almost 6,000 years. So after 6,000 years, I have 50 carbons left. Divided in half, I have 25 after 2. Divided in half again, I have about 12 or 13. Divided in half again, I have 6. Divided in half again, I have 3. Divided in half again, I have 1 or 2. Divided in half again, I have 1. So it takes almost 40,000 years for the carbon-14 to decay into nitrogen. It's pretty cool. All right, how long does it take for a sample of an isotope to decay? So again, these each happen instantly when they do happen, but you can see if you watch up here, you can see that I haven't hit 1 half-life, but some of them have already changed. It's just at the half-life, half of them have changed. All right, so the time it takes for a specific amount of radioactive material to decay is measured in a unit called a half-life, or the plural is half-lives. The half-life, which is abbreviated T sub 1/2, so half the time, of a radioisotope is the amount of time required for 1/2 of the radioactive nuclei of the parent substance to decay into the daughter substances. So if you start with 100% parent substance, you will have the following over time. After 1 half-life, half is remaining. After 2 half-lives, a quarter. After 3, an eighth, or 12.5%. After 4, you have only 6.25%. The half-life varies with different radioisotopes. So percentage of decay in an isotope sample with a half-life of 1 year. So after 1 year, you have half. After 2 years, you have 25%. After 3 years, 12%. 4 years, 6%. 5 years, 3%. 6 years, 1%. And after 6 years, you have the amount that is left. And then, of course, it keeps getting tinier and tinier. So you can really see from this illustration how much smaller it gets every year, just like you could really see on the graph how it gets way smaller, kind of smaller, little smaller, and then it kind of levels out on the graph. So just 2 different representations of that. Okay, so in our notes, I said how long does it take for a sample of an isotope to decay? Parent isotope, original isotope, changes into a daughter isotope almost instantly in an atom. However, it takes a long time for a whole sample, or like 10 pounds, to decay. The time it takes for 1 half-life of the radioactive isotope in a sample to decay into another atom is called the isotope's half-life, or T sub 1/2. And then I put these down along with the fractions, because sometimes with this it works better to work with the fractions. All right, and yep, now we'll do some problems. So you can calculate the amount of material present if you know the half-life. If you are given the half-life for decay of a particular radioisotope, then you can calculate how much of that radioisotope remains after several half-lives. And we call that the fraction remaining. So how much is left is the fraction remaining, or FR, and it equals 1/2 to the exponent n, or to the nth power, where n equals the number of half-lives. Okay, so let's do a sample problem. For example, carbon-14 has a half-life of 5,730 years. If you start with a 2.00 times 10 to the negative 6 grams of carbon-14, how much will you have after 17,190 years? List what you know. You know how much time has gone by is 17,000 years. The half-life, or the time for it takes for the amount to be divided in half, is 5,730 years. And the amount of substance that you have is 2 times 10 to the negative 6 grams, which you might want to put in your calculator just as a decimal. And so let's double check. Yeah, so you might want to just put it in your calculator as a decimal. All right, so calculate the number of half-lives. If you think you can do it, hit pause and do it. And, oops, I think I copy-pasted wrong. All right, so to find how many half-lives there are, you take the amount of time that's gone by, and you divide it by how long it takes for a half-life. So 17,000 years went by, almost 6,000 years is a half-life. You divide them, 3 half-lives went by. And you can calculate the fraction remaining from the number of half-lives. So the fraction remaining is 1/2 to the nth power. So 1/2 to the third, because there were 3 half-lives. And your answer is 1/8. So there's 1/8 remaining from the original substance. Okay. Multiply the fraction remaining by the initial amount. N sub O is the initial amount. N sub 1 is the final amount after time t. So N sub t equals the fraction remaining times N sub O. In other words, 1/8 times 2 times 10 to the negative 6 grams give you an answer of 2.5 times 10 to the negative 7 grams. Honestly, I think there's an easier way to do it. I wanted to show you this way first. Some people like this way. Another example. You have 10 grams of thorium-234. How much remains after 48.2 days if the half-life is 24.1 days? Okay, finding how many half-lives went by is the same. So hit pause, try and do that. Answer is, I wrote down everything I know. How many half-lives? I take how much time went by divided by how long each half-life is. So I know there's 2 half-lives. Then what I would do is I said, okay, they gave me 2 grams, divide it by 2. So after 1 half-life, it's 5 grams. Okay, divide it by 2 again, and I know after 2 half-lives, there's 2.5 grams. So just divide it by 2 every time you have a half-life. So if I have 3 half-lives, divided by 2, divided by 2, divided by 2. If I have 4 half-lives, divide by 2, divide by 2, divide by 2, divide by 2. Okay, I think it's easier. I don't care which way you do it. All right. Unstable nuclei may undergo a series of decays before becoming stable. You may be under the impression that all stable nuclei, or radioisotopes, become stable after one instance of decay. This may be true for isotopes of low mass or low atomic number elements, so atomic number less than 20, but it is usually not true for high mass or high atomic number isotopes. Often, these radioisotopes undergo a series of decays over time. Each step usually has a different half-life. For example, uranium-238 decays in 14 different reactions to ultimately become lead-206, which is stable. Each step in the decay process has a different half-life. Some half-lives are in minutes, some are in days, some are in years. And so we have our timeline here. I'm going to show you this first. So you start with uranium-238, okay? And we are going to be changing into all of these elements along the way. So, uranium-238. It takes 4.5 billion years. Okay? It takes that long for it to decay into thorium. Once it's thorium, it takes like 24 days to turn into protactinium. It only takes a minute to turn into uranium-234. So it started out as uranium-238, and now it's going to turn into uranium-234. Then it takes, just 200,000 years to change into thorium-230, another 83,000 years to turn into radium-226, about 1,600 years to turn into radon-222, almost 4 days to turn into polonium-218, 3 minutes to turn into lead-214, about a half an hour to change into bismuth-214, about 20 minutes to turn into polonium-214, another 1,500 years to turn into lead-210, 22 years, bismuth-210, 5 days, polonium-210, and 140 days to turn into the final product of lead-206. All right, there you go. There's my arrows. Oh, I had to go through it first before my arrows popped up. All right, so is our final goal. We're starting out with uranium. It bumps back. After it turns into thorium, bumps back into uranium, turns into thorium with a different mass number, turns into radium, goes into radon, bounces over here. You can see you got some bouncing back and forth until finally it becomes lead. So it's kind of cool. All right, and so for the notes for that, I just added half-life varies with different radioisotopes. Low mass or low atomic number elements may only go through one round of radioactive decay, but high mass or high atomic number isotopes go through many. Each step usually has a different half-life. And then I just put that last paragraph on there of the example we went through. Unstable nuclei decay by giving off radiation. So here's our review slide. Radioactivity is caused by decay of nucleus, which occurs when unstable nuclei lose protons or neutrons. Nuclei are unstable when there are a relatively high number of protons per neutron. Unstable nuclei decay to stable ones by giving off radiation. Radiation is particles, energy, and/or heat. You can have alpha emissions, which is the nucleus, so like that helium, 2 protons, 2 neutrons. Beta emission, which is a high-speed electron or positron. Gamma emissions, which are electromagnetic waves. Other electromagnetic waves, if you're kind of wondering what those are like X-rays, light, so like the different colors we can see of light, microwaves, radio waves, all those. Radioactive emissions can change the composition of the nucleus. The time of radioactive decay is measured in half-lives. Heavy isotopes change to stable ones in a series of radioactive decays. And that's it for this one.